Good afternoon, everybody. Today I am going to present a lecture on the topic control charts and ISO. So, let me tell you first what are control charts. A control chart is a statistical tool which is used to distinguish between variation in a process resulting from common causes and variation resulting from special or assignable causes. It presents a graphic display of process stability or instability over time. So, what happens is that if all the points in the control chart they are within the limits, that is within the upper control limit and lower control limit, then we can say that the process is stable or all the causes are common causes. But if points they go beyond the limits, that is if the point is outside the upper control limit or below the lower control limit, means that there is some assignable cause which has result in the instability of the process. Now, we can say that no two products are exactly alike because of slight difference in material, workers, machine, tools and other factors. Means to say that if we observe any two products, we will notice that the two products will never be same. There will be a slight difference in that product in between the two, and the reason is that either the material which we are going to use is different, or the workers which are manufacturing that product, there might be difference in the workers working over that product, and the machine tools and the machines which we are using for the manufacturing, there will be a difference in that. That is why these all causes are called as common causes. We can't neglect them. These causes can't be neglected because these are random. Now, the common causes of variation, they are based on random causes that we cannot identify. It is really very difficult to identify these causes, and these type of variations, these are unavoidable. We can't avoid them, and these are due to the slight difference in the process, manufacturing process. Now, for example, if the average bottle of a soft drink, say Epi Fizz bottle, it contains 16 ounces of liquid, we may determine that the amount of natural variation or the natural cause is between 15.8 and 16.2 ounces, means plus minus 0.2, we consider it as a common cause of variation, we cannot neglect it, and we consider it as a random cause. Now, second one is the assignable cause. Now, the second type of variation that can be observed involves variations where the causes can be precisely identified and eliminated. These are called as assignable causes of variations, means to say that these causes we can identify them and we can also eliminate them. Now, the reason for this example of this type of causes may be variation in poor quality in raw materials, either the raw material which we are using is of poor quality, or an employee or worker who is working on that product, he needs training, he is unskilled, or the machine which is being used for manufacturing of that product, it is not accurate, it needs repair. So, these are the assignable causes of variation which can be identified and which we can also eliminate. Now, say taking the same example of the soft drink bottling operation, the bottle which is filled with 15.6 ounces of liquid would signal definitely a problem, because the variation which was tolerable was plus minus 0.2, either 15.8 or 16.2. So, this has crossed the 15.8 limit. So, this is a result of the assignable cause of variation. So, the problem is definitely there. So, the problem may be the cause of the machine, maybe need to be readjusted, or the worker is unskilled. So, this is an assignable cause of variation. So, this is the control chart which shows that all the points, these are close to the control line, control limit, except one point which is above the upper control limit. That point is point A, and this is definitely the assignable cause of variation. Now, the one goal of using a control chart is to achieve and maintain process stability. Now, the process stability is defined as a state in which a process has displayed a certain degree of consistency in the past and is expected to continue to do so in the future. Means a process is stable if all the points, all the data in the process, they are within the control limits. Means all points are, they are within the upper control limit and the lower control limit. So, the process which is having all its points within the control limit is a stable process. Now, this consistency is characterized by a stream of data, I have already told you, which is falling within the control limits, which is based upon plus minus 3 sigma limits of the central line. Now, what is the purpose of control charts? Why control charts are required? Now, control charts, they are an essential tool of continuous quality control, means these help us in the quality control, because from the control chart we can see that whether the process is stable or not by viewing the data which is being falling on the control charts. The control charts, they monitor processes to show how the process is performing and how the process and capabilities are affected by changes to the process. This information is then used to make quality improvements. Means if we, from the control charts we can see that if all the data it is within the limits, we can say that the process is stable and the quality is improving. If during the process we make changes and on applying that data on the control charts, if we see that some data has gone out of the limits, then we can say that there is definitely a change is going to be done in the process as the process is becoming unstable. The control charts, they are also used to determine the capability of the process, whether process is capable or not. They can also help identify special or assignable causes of factors which hinder the performance, which stop the performance of the process. Now, what is process capability chart? A process capability is the ability of a production process to meet or exceed preset specifications. Means with the help of process capability chart we can check that where the specifications which are defined, that process is exceeding or meeting the specifications, given specifications or not. Now, process capability analysis is used to adjust the process until virtually all of the product output meets the specifications. Means in the what happens in the analysis of the process capability, we do what is that we see that whether the product output it is meeting the specifications or not. If it is meeting the specifications, then it is okay, but if it is not meeting the specifications, then we will do a slight adjustment in the process so as to make it stable. Now, the process capability chart, it contains a normal curve which is superimposed over a histogram of the data followed by several statistics. I can show you the process capability chart. This is the process capability chart, we will discuss it later. So, the process is said to be capable if its output falls within the specifications virtually 100% of the time. Now, for example, the specifications for the width of a machine part, it may be specified as 15 inches plus minus 0.3, means plus minus 0.3 is the normal variation. This means that though the width of the part it should be 15 inches, but it is acceptable if it falls within the limits of 14.7 inches and 15.3 inches, but if it goes beyond, then we can say that it is not acceptable and the process is unstable. Similarly, for cocoa fizz or epifizz bottle, the average bottle fill may be 16 ounces with the tolerance of plus minus 0.2 ounces, means plus minus 0.2 ounces tolerable, but although the bottle should be filled with 16 ounces of liquid, but amount can be as low as 15.8 or as high as 16.2, means it is acceptable if it is within the 15.8 or 16.2 range, but if it exceeds 15.8 or 16.2, we can say that the process is unstable or there is some assignable cause of variation being there. Now, what is process capability? Process capability is measured by the process capability index CP, which is computed as the ratio of the specification width to the width of the process variability. Means CP is equal to specification width over process width. Specification width is the difference between the upper specification limit and the lower specification limit of the process. It is divided by 6, it is called as CP. Now, this is the process capability chart. We have seen that there is a histogram with the mean value given as 44.788 and the plus 3 standard deviation, that is upper specification limit is 61.498 and the lower specification limit, that is minus 3 sigma deviation, is 28.077. Now, how do control charts work? The control charts show if a process is in control or out of control. That I have already told you that if the points they are falling within the limits, we can say that process is in control, and if the points are out of the limits, beyond the limits, we can say that process is out of control. They show the variance of the output of a process over time, such as measurement of width, length or temperature. Now, control charts, they compare this variance against upper and control limits. I have already told you, to see if it fits within the expected levels or not. Now, if the data it fits within the limits, then we can say that the process is in control. If however, the variance it falls outside the limits or has a number of non-natural points, then the process is out of control. Now, the area between each control limit and the center line is divided into thirds. This is the thirds: zone A, zone B, zone C. The third closest to the center line is referred to as the zone A, and the next third is the zone B, and the third closest to the control limit is the zone 3. Now, the zone A is also referred to as the 1 sigma zone, zone B is the 2 sigma zone, and zone C is the 3 sigma zone. And sigma is the Greek letter for S, and it is used in this context to denote the spread of data, how much data is being spread on the chart. Now, if the zone A has 68.3% of the data included in it, zone B has 95.5% of data spread in it, and zone C has the 99.7% of the data spread in it. Now, the standard control limits, they are located 3 sigma away from the center line, as I have already shown you, which is the zone C. It is the 3 sigma away from the center line. Now, the center line is also called as the control line. These 3 sigma limits, they are called as the control limits or 3 sigma zones. Statistics tell us that in normal data dispersion, we can expect the following percentage of data be included in the sigma levels. In the first sigma, we can say that 68.3% of the data is covered in the 1 sigma zone, 95.5% of data is included in 2 sigma zone, and 99.7% of data is included in 3 sigma zone. That is, we can expect 99% of the process outcomes to be within the 3 sigma control limits. Means we can say that if the process is in control, it means that 99.73% points will be within the control limits. Now, how control limits are generated? The control limits, they are calculated statistically from the data which we are providing. Now, these are referred to as the lower control limit, which is LCL, and the upper control limit, which is UCL on a control chart. Now, these limits, they are set 3 sigma apart by default. Now, an outcome beyond the control limits results from a special cause that I have already told you. If the data falls outside the limits, we can say that there is a some assignable cause of variation in that data. The special causes indicate that there have been one or more fundamental changes to the process and the process is out of control. This is the data showing assignable cause of variation at point A. Now, what are the types of control charts? Now, there are two main categories of control charts, those that display attribute data and those that display variable data. Now, first we will discuss the attribute charts. Now, attribute charts are also known as count charts and attribute data is also known as discrete or separate data. Attribute data is measured only with the whole numbers. There is no fractions we can use in them, only whole numbers are being used in case of attribute data. An example of this includes that is acceptable versus non-acceptable, and whether the data is acceptable or not, and the forms completed with errors versus without errors, number of prescriptions or number of observations with errors or which is versus without errors. Now, charts which are used for attribute data, they are called as, they are the defect charts and reject charts. We will discuss these charts one by one later on. Next is the variable charts. Variable charts, they are based upon the variable data which keeps on varying and that can be measured on a continuous scale. That is not separate, we can say that is not discrete, which is not discrete, it is a variable charts. Now, example of this is the weight, volume, temperature or length of stay. And these can be measured to as many decimal places as necessary. Now, the charts which are used for variable data, they are the individual charts, average charts and range charts. We will discuss the variable data charts first of all. So, there are three charts which discuss the variable data charts, they are individual charts, average and range charts. Now, what the variable data, it requires the use of variable charts, as the variable charts are easy to understand and use. So, this is the chart showing the variable data, and if the sample size is 1, then which chart we are going to use? We are going to use the individual chart, individual range chart or moving range chart, and if the sample size it is small, usually between 3 to 5, then we are going to use the X bar chart, or second option is the X bar chart along with range chart. And if the sample size it is large, it is greater than 10, then we are again using the X bar chart or X bar chart with standard deviation chart along with the standard deviation chart. Now, first comes the individual chart, I chart. Now, the I chart is also referred to as the individual chart, individual item chart, means in this we plot the data of the individual item. Now, the X refers to a variable X. Now, individual charts, they plot the process results varying from over time, means individual observations are plotted on the I chart. We never plot averages in this chart, only individual observations with time they are plotted on this chart. We do not plot averages in case of the I chart. Now, these individual charts, they are used to plot variable data collected chronologically from a process, such as the measurement of a part or any machine part over time. Now, this is the individual chart or I chart, it shows the various observations in minutes being done on the, or we can say that this is the chart of a patient waiting time, how much time is patient waiting for its turn to come, this is in minutes. Next comes the average chart or X bar chart. Now, the average charts, they are made by simply taking the averages of a number of subgroups, means there are 1 to 3 groups, subgroups, and each having the individual group, individual mean to say observations, and we will take the average ordered observations of one subgroup, and by considering the averages of different subgroups, we plot it on the chart, and that chart is called as the average chart. Now, average chart is called the X bar chart because in statistical notation, a bar or a line over the variable, it symbolizes the average of that variable or x. Now, an x bar chart, it is a variable control chart that displays the changes in the average output of a process. In the individual chart, we only plotted the individual observations, but in x bar chart we display the changes in the average output of a process. This chart shows how consistent and predictable a process is at achieving the mean. Means this process chart tells us that how is whether that chart process it is achieving the mean value or not, it is coming close to mean or it is going farther to mean. Now, the x bar charts, they measure variation between subgroups, means with the help of x bar charts we can also measure the variation within the subgroup, and these are done by pairing the x bar charts with the either standard deviation chart or range charts, which measure the variation within the subgroups. So, this is the x bar chart. We are plotting the average values of the different subgroups on this x bar chart. Next comes the range chart, R chart. Now, the range chart, it can be combined with either individual chart or x bar chart. The chart names combine the corresponding chart initials. Now, the range charts, they measure the variation in the data, means these charts measure the variation within the subgroups. Now, example is a weather report in the newspaper that gives the high and low temperatures each day, and now the difference between the high and the low is the range for that day. So, this is how we calculate the range. The difference between the higher value and the lower value gives us the range of that data of that process. Now, this is the range chart or R chart, which tells us about the higher and lower values, difference between the higher and the lower values. Now, next is the moving range chart or MR chart. Now, this type of chart, it displays the moving range of successive observations, means a moving range chart can be used when it is impossible or impractical to collect more than a single data point for each subgroup. In that case, we use the moving range chart. Now, the moving range chart, it displays variability among measurements based on the difference between one data point and the next, means the difference between the higher and the lower value, that gives us the range, and by plotting it on the chart we get the moving range chart. This is the moving range chart. So, this shows the difference between the higher and the lower next lower value, which is being plotted on this chart. Next comes the individual and range charts, IR charts. Now, this pair of variable control charts is often offered together for quality control analysis. Means we use this for the purpose of quality control. Now, the individual chart, which is the upper chart in the figure in the next slide, displays changes to the process output over time in relation to the center line, which represents the mean. So, this is the top one is the individual range chart, and the second the moving range chart, which is the lower chart in the figure in the next slide. It analyzes the variation between the consecutive observations, which is a measure of process variability. So, this is the first one is the individual range chart, and second one is the moving range chart. Next one is the average and range charts, means X bar and R charts. A variable and range control charts, they are often displayed together for quality control analysis. Now, the X bar chart, which is the upper chart in the figure in the next slide, this is the X bar chart, upper one, is a graphic representation of the variation among the subgroup averages. It tells us about the variation between the subgroup averages, and the R chart, which is the lower chart in the next figure, in the next slide, it looks at variability within these subgroups. Mean to say that the X bar chart, it tells us about the average between the subgroups, and the range chart, it tells us the range within the subgroups. Variation, that is range means that is the variation within the subgroups. Now, the variation within the subgroup is represented by the range R. Now, the X bar standard deviation chart, that is X bar and S chart. Now, this pair of variable control charts is often displayed together for quality control analysis. Now, the X bar chart, which is the upper chart in the figure in the next slide, the top one is the X bar chart. It displays the again the variation in the means between the subgroups. It displays the variation in the means between the subgroups, and the S chart, that is the lower chart in the figure in the next slide, it looks at variability within the subgroups. Means both the R and the S charts, they show us the variability within the subgroups. Now, in this pair of charts again, the variation within the subgroup is represented by the standard deviation or the standard deviation chart. And the standard deviation is plotted on the y axis and is a measure of the spread of values for each subgroup. Now, the center line is the average or mean of the subgroup standard deviations. Next comes the attribute charts, that is defect chart and reject chart. Now, from this table we can see that there are two types of attribute data charts. One is the defects data chart, another one is the rejects data chart. In case of defect data, if the sample size is constant, we use C chart, and if the sample size it varies, then we use the U chart. Now, in case of rejects data chart, if the sample size it is constant, but it is usually greater than equal to 50, then we use the NP chart. But if sample size is varying, is a variable, and the size is usually greater than 50, then we use the P chart. So, we will discuss all these four charts one by one later. Now, the defects chart. Now, these attribute charts, they are for cases in which the possible occurrences are infinite. Means that if the occurrences are infinite, means we cannot count these occurrences, then we use the defects chart. And these chart, they count the number of non-conformalities, that is defects within item. Means how many defects are there in that item, that is being counted by the defect chart. From the name clear that defects means it counts the number of defects in that item, in the particular item. Next comes the rejects chart. Now, these attribute data charts, they are for the cases in which rejected whole units are counted. Now, the first case was when the occurrences are not countable, they are infinite. And the second case in the reject chart is that the reject chart is used when the units they can be counted, means they are finite. Means these figures can be described as ratios instead of just counts. Now, these count the number of rejected units in a subgroup. So, reject chart, they count the number of rejected units in a subgroup. Now, first come the defects chart. There are two types of defects charts, that is the C chart and the U chart. Means the C chart, it refers to count of defects in a subgroup of constant size. Means to say that C chart is used where the subgroup size is constant, and the U chart, it is a per unit count, and it is used where the subgroup size is variable. This is the difference between the two charts, C and U charts. Now, a C chart or a count chart, it is an attribute control chart that displays how the number of defects is collected for the area of opportunity in each subgroup. Means it tells us that how many defects are there in the subgroup or in that individual item. Now, this area of an opportunity, it can be either a group of units or just one individual unit on which the defects are to be counted. Now, the C chart, it is an indicator of the consistency and